Out in the depths of space, the James Webb Space Telescope is living up to its hype. From inexplicably bright galaxies to the potential discovery of life on alien planets, and even challenging our understanding of the universe's beginnings, this powerful telescope has stunned the scientific community. It has provided us with incredible insights, including multiple structures that shouldn't exist. However, this is where the problem lies. The James Webb Space Telescope is upsetting the apple cart, making us realize that we may need to rewrite textbooks about the origins of the universe. To understand this dilemma, let's start by taking a quick look at the Big Bang, our best supported theory of the universe's origin. Originally, the Big Bang was a simple idea that grew from three interconnected facts and Einstein's general theory of relativity. According to relativity, a universe filled with a uniform distribution of matter and energy cannot remain stable in a static configuration. The fabric of space in such a universe must either contract or expand. Observationally, there are spirals and ellipticals in the sky lying well beyond the Milky Way. Their distances can be measured, and the light from these spirals and ellipticals appears to be redshifted. More distant objects exhibit greater redshift in direct proportion to their distance, which is consistent with an expanding universe. By combining these facts, we can conclude that if the universe is expanding today, it must have been smaller and denser in the past. The first person to synthesize this information was Georges Lemaitre in 1927. Others, like Howard Robertson in 1928, Edwin Hubble in 1929, and Arthur Walker later, reached the same conclusion. Over time, more consequences of the Big Bang were derived, including the idea that the early state of the universe was hotter and denser. As the universe expanded, it cooled, allowing the formation of neutral atoms and the eventual creation of stars, galaxies, and cosmic structures. However, this understanding of the Big Bang is not the whole story. Three additional ingredients have been discovered: dark matter, which clumps and gravitates but does not collide with normal matter or photons; dark energy, which behaves as energy inherent to space itself; and cosmic inflation, which limits how far back into the past we can extrapolate the hot Big Bang. These ingredients allow us to describe the universe's conditions at the start of the Big Bang, including how hot and dense it was. Yet, despite the observational evidence supporting this model, it may not be fully correct. Each time we observe the universe in new ways, we must check if what we see aligns with this model. This is where the James Webb Space Telescope has been instrumental. Its observations of the early universe have raised doubts about current cosmological models, suggesting that our understanding of the Big Bang may need revision. The James Webb Space Telescope has gone further than any other NASA instrument. As Matt Greenhouse, a James Webb senior staff member, noted, it has given humanity its first high-definition view of the infrared universe. Thanks to its capabilities, we're discovering and characterizing galaxies from the very early stages of cosmic history. Before James Webb, we had only one confirmed galaxy, GNZ 11, from about 400 million years after the Big Bang. Now, more than 100 galaxy candidates from this early epoch have been identified, with several confirmed. These early galaxies have puzzling properties. They appear to be massive, bright, rich in heavy elements, and actively forming stars, properties that challenge current theoretical models of how galaxies evolve. There are limits to how fast material can accrete onto these objects, and while some conditions may allow temporary overcoming of these limits, they shouldn't persist over long timescales. James Webb's findings have caused a stir, leading some to question our understanding of galaxy formation and evolution. Not only are there inexplicably large galaxies, but James Webb has also discovered massive black holes from the universe's early periods. The first quasar, J119, found by the telescope, was 10 million times the mass of our Sun and existed just 570 million years after the Big Bang. In April 2023, the telescope broke its own record, discovering a black hole in the galaxy GNZ 11, 13.4 billion light-years away. This black hole is around 6 million times the mass of the Sun, challenging current theories about how such massive objects could form so early. In addition to these groundbreaking discoveries, James Webb has found thousands of Milky Way-like galaxies in the early universe, far more common than previously thought. These galaxies, with delicate spiral arms, shouldn't exist in a period dominated by galactic mergers. Such discoveries are deepening the mystery of how galaxies and life first emerged in the universe. Webb's observations have also revealed entirely new, unexplainable objects. For example, in the Orion Nebula, it found pairs of Jupiter-mass objects too small to be stars but unlikely to be rogue planets. These findings may indicate new planetary or star formation mechanisms. Closer to home, the telescope has revolutionized our understanding of Saturn's rings, showing they are much younger than previously thought. It captured detailed images of Uranus and weather systems on Mars. The James Webb Space Telescope's ability to study distant planets, particularly exoplanets, holds profound implications for our understanding of planet formation and the potential for life beyond Earth. Exoplanets are planets that orbit stars outside of our solar system, and studying them offers a unique opportunity to learn about planetary systems that might be vastly different from our own. Before the advent of telescopes like the James Webb, scientists could only speculate about the conditions on these distant worlds. Now, with its powerful infrared capabilities, JWST is providing concrete data, allowing scientists to peer into the atmospheres of these planets and uncover details that were previously inaccessible. One of the most exciting developments in exoplanet research is the ability of the James Webb Space Telescope to detect chemicals in the atmospheres of distant worlds. These chemicals can provide critical information about the conditions on the planet, such as its temperature, composition, and potential habitability. Most importantly, the telescope has detected key signs of life, or biosignatures, in the form of carbon-bearing molecules and methane. These molecules are considered fundamental building blocks for life as we know it, and their presence in the atmospheres of exoplanets suggests that the conditions necessary for life could exist in other parts of the universe. A particularly compelling example is the detection of carbon-bearing molecules and methane on the planet K2-18b, an exoplanet located about 120 light-years away from Earth. K2-18b is classified as a mini-Neptune, meaning that it is a gas giant smaller than Neptune but still significantly larger than Earth. The planet is located in its star's habitable zone, the region around a star where conditions might be right for liquid water to exist. The discovery of methane in K2-18b's atmosphere is especially intriguing because, on Earth, methane is produced by biological processes. While this does not necessarily mean that life exists on K2-18b, it does raise the tantalizing possibility that the planet could harbor conditions suitable for life. The presence of methane on K2-18b has sparked significant interest within the scientific community. On Earth, methane is primarily produced by living organisms, particularly microorganisms, though it can also be produced through non-biological processes, such as volcanic activity. The discovery of methane, in combination with other molecules such as carbon dioxide and water vapor, strengthens the hypothesis that K2-18b could have a habitable environment. In fact, some scientists have speculated that K2-18b, like many exoplanets, extends far beyond the search for extraterrestrial life. These discoveries also offer valuable insights into the processes of planet formation and evolution. By studying the atmospheres of exoplanets, scientists can learn about the various stages of planetary development, from the accumulation of gases and dust in the early stages of a planet's formation to the chemical reactions that occur as the planet evolves. This knowledge can then be applied to our understanding of how planets, including Earth, formed and developed over billions of years. In addition to providing clues about the formation of planets, the study of exoplanet atmospheres can also help scientists understand the diversity of planetary systems in the universe. The discovery of exoplanets with atmospheres rich in methane and other carbon-bearing molecules suggests that the conditions for life might not be as rare as we once thought. In fact, it is becoming increasingly clear that there could be many planets in the universe with the potential to support life. The James Webb Space Telescope is uniquely equipped to explore these possibilities, thanks to its ability to detect and analyze the faint light emitted by distant exoplanets. By studying the light that passes through the atmospheres of these planets, the telescope can determine the composition of the gases present, providing critical information about the planet's environment. Beyond K2-18b, the James Webb Space Telescope has detected potential biosignatures in the atmospheres of several other exoplanets. In some cases, the telescope has found evidence of water vapor, which is another essential component for life. The discovery of water vapor in the atmosphere of a planet located in its star's habitable zone is particularly exciting because it suggests that the planet could have the right conditions for liquid water to exist on its surface. This, in turn, raises the possibility that the planet could be capable of supporting life, either in the form of microorganisms or more complex organisms. The discovery of carbon-bearing molecules, methane, and water vapor in the atmospheres of exoplanets is a major step forward in the search for life beyond Earth. While these findings do not provide definitive proof of extraterrestrial life, they do suggest that the conditions necessary for life could be more common in the universe than we previously thought. The James Webb Space Telescope has opened a new window into the study of exoplanets, allowing scientists to explore these distant worlds in unprecedented detail. As the James Webb Space Telescope continues to observe exoplanets and their atmospheres, it is likely that we will discover even more clues about the potential for life elsewhere in the universe. The telescope's ability to detect and analyze biosignatures, such as methane and carbon-bearing molecules, is a powerful tool in the search for extraterrestrial life. Each new discovery brings us one step closer to answering one of humanity's most fundamental questions. Are we alone in the universe? The James Webb Space Telescope is revolutionizing our understanding of exoplanets and their potential to harbor life. The detection of chemicals like carbon-bearing molecules and methane in the atmospheres of distant worlds, particularly on planets like K2-18b, raises the tantalizing possibility that life could exist elsewhere in the universe. As the telescope continues to study these distant planets, it will provide valuable insights into the processes of planet formation and evolution, and it will help us better understand the diversity of planetary systems in the universe. The search for life beyond Earth is still in its early stages, but the James Webb Space Telescope has already provided us with crucial evidence that the conditions necessary for life could be more widespread than we ever imagined. The James Webb Space Telescope has revolutionized our view of the universe, providing unprecedented insight into the cosmos and forcing us to rethink fundamental questions. From the origins of the universe to the potential discovery of life, it is challenging held beliefs and reshaping our understanding of the cosmos. As we continue to explore space with Webb, we can expect even more discoveries that will further transform our view of the universe and our place within it. The James Webb Space Telescope, JWST, not only enhances our understanding of distant galaxies and potential life, but also deepens our insights into the fundamental laws of physics. Its advanced instruments allow astronomers to investigate phenomena that were previously shrouded in mystery. For instance, JWST's sensitivity to infrared light enables scientists to explore the cosmic web, the large-scale structure of the universe. This web comprises filaments of dark matter and gas, serving as the scaffolding upon which galaxies are built. By studying the cosmic web, researchers can gain valuable insights into galaxy formation and evolution over cosmic time. JWST has the potential to identify ancient galaxies that formed shortly after the Big Bang, shedding light on how they contributed to the overall structure of the universe. This understanding is crucial for piecing together the timeline of cosmic history, from the formation of the first stars to the intricate dance of galaxies we observe today. Furthermore, JWST is revolutionizing our study of stellar life cycles. Stars undergo dramatic transformations from birth in nebulae to their eventual demise, which can lead to the creation of supernovae, neutron stars, or black holes. By capturing detailed images of star-forming regions and supernova remnants, JWST allows astronomers to study the processes that govern stellar evolution. This can help answer questions about the distribution of elements in the universe, as massive stars are responsible for creating many of the heavier elements found in nature. The telescope's exploration of star formation also provides clues about the environments that could support planetary systems. Understanding how stars and planets form together in dense molecular clouds informs our theories about the conditions necessary for life to develop. As JWST observes these regions, it may discover new insights into how the building blocks of life, such as organic molecules, are synthesized in the cosmos. In addition to its contributions to astronomy, JWST has implications for technology and engineering. The design and construction of the telescope involved innovative techniques and materials that push the boundaries of what is possible in aerospace engineering. For instance, its large, segmented mirror allows for unprecedented resolution and sensitivity, which could inspire future missions and instruments. The knowledge gained from JWST's development will inform the next generation of telescopes, enhancing our ability to explore the universe.